Now we come to the experiment section. This is the evidence section, essentially. In here, the paper tries to prove the thesis. If you see here, I think this is the key statement. The learning rate of each model was manually tuned for the best perplexity on a 5% held out sample of WebText. Now, the key term to define here is perplexity. I'll show you a graphic so that we understand perplexity well. So, perplexity measures how confident the model is at predicting the next word. Now, if the model is highly confident, then it would probably say that this word, like for example, if the starting two words is the cat and it's very confident that sat is the next one, we are going to clearly see the difference between probabilities of the ones which are rejected versus the ones which are higher. And then if the model is confused, it'll probably have the probabilities which is fairly close by. And so that is high perplexity, this is low perplexity, which means the model is more confused. Now, why this matters is it tells us that whether the model is predicting token cleanly on unseen text. Low perplexity means the base language model is sharper before any task-like prompting. It is the effective number of choices the model feels it has for the next word. Good language models keep that number low, and that is why we are using perplexity as a key way to understand performance of the model. Now, going back to our paper, despite all of the tuning, the model still underfit WebText. So, what it's saying is even for the 1.5 billion parameter model, that massive for its time, it has not fully captured the patterns in WebText. When a model that big is still underfitting, the immediate signal is the model needs to be bigger. So essentially, the model has not run out of patterns to learn from the data. And so the clear way to scale this is increasing the model size. More parameters, more compute should reliably keep improving performance. That is the key intuition from this statement. Now, with the experiments, the key framing for all of these experiments is zero shot. That means they are seeing novel tasks which they have not been trained on. And it is a frozen GPT-2, so that it's not been fine-tuned. Just task-shaped text prompts. With that, what we are seeing is, first, scale improves the base language model, as we just established from here. Perplexity keeps dropping across data sets. Now, I'm not going to go through each and every of the experiment because we will not have that much time. I'm just going to use a visual. Overall, we see perplexity keeps dropping across data sets. For the children's book test, keeps getting better. It was already strong. Vinograd gets better. Question and answers gets better. The stronger the token predictor becomes, the more task behavior you can pull out without fine-tuning. That is essentially the key takeaway. Some tasks show the model is using the context, and the biggest one is this long-range context test. In here, the benchmark essentially asks the model to predict the final word of a paragraph. So only if the model understands the entire paragraph, which at that time would use 50 plus tokens, then the model would be able to predict the final word. GPT-2 had a big jump here. It's one of the clearest signs that the context window is real. Now for some of the other tests, conversation question answering, it's weaker but same direction. A pure language model can read a passage and answer about it, even if it is not as good as supervised systems. Third, the behavior is uneven and prompt sensitive. Summarization is weak as raw continuation, but then it improves when the prompt ends with TLDR. And then translation is limited because, again, WebText is mostly English. Natural questions does show that there are facts inside weights, but this is not reliable retrieval yet. And this next section, which is very interesting, is generalization versus memorization. Now imagine a model learning from a huge library of books. This section essentially looks at data overlap. The same sentence or very similar phrases appearing in both training data and test data. Now the big question it's trying to answer is when these models perform well on test, is it because They truly understand the language and can generalize, or are they just memorizing answers they have seen before? Think of it this way. Memorization is like studying for a test by remembering the exact answers to practice questions. Same questions on test day, you do great. Rephrased questions, you struggle. Generalization is truly understanding the concepts. You can answer practice questions and you can also answer new, never before seen questions because you grasp the underlying ideas. Now, this section finds that some impressive performance may be due to overlap. It makes generalization look stronger than it is, but the benefit from overlap was not massively larger than the baseline, as you can see here. So memorization is not the whole story. The model is doing something else. It can generalize and it can understand the relationships and patterns in language. Now you can see the text here. Another potential way of determining whether the performance of WebText LMs is into memorization is inspecting their performance on their own held out set. Now the key bit here, which is funny, but let's get into it, is GPT-2 is also able to write news articles about the discovery of talking unicorns. So what it means is a model takes a prompt like, in a shocking finding, scientists discovered a herd of talking unicorns, and continues with a creative, believable story. Now, that's not memorization. The model likely never saw that exact story. Instead, it is using generalized understanding of language, storytelling, and fantasy concepts to create something new. That is generalization in action. Now, let's talk a bit about this statement, which is a fairly loaded statement. As shown in Figure 4, performance on both training and test sets of WebText are similar and improve together as model size is increased. This suggests even GPT-2 is still underfitting on WebText in many, many ways. I'll not go into details about underfitting and what do they mean. In the context of this paper, when performance on both training and test sets of WebText are similar and both improve together as model size increases, it essentially tells us that we have not hit the point where bigger models stop helping. As of when the paper came out, the models were still underfitting their full potential. More pre-training would unlock even better performance. And you can see here how the model performance is changing as the parameters improve. Now, the key section is there is data overlap is something to watch out for. The model is already generalizing and not just memorizing. And even with their impressive abilities, there's always room to grow. Now we come to the FAQ section. These are some of the questions that I had while reading the paper that I put in this section. Now, the first question, how does this paper connect to current pre-training methods? Now, GPT-2 says if the model still underfits WebText, scale should help, as we have seen. But the modern view is a bit more nuanced. There's a new paper called Chinchilla, a 2022 DeepMind paper, showed how many big models were undertrained for their compute. As in, more tokens mattered, not just more parameters. So today, pre-training still matters, but progress also comes from better data curation, code and metadata, multimodal data, post-training, and test time reasoning. So at the time of GPT-2, it was scale still helps. Now we know from the Chinchilla paper and today, we spend compute on both parameters and data, and not just parameters alone. Next question. What changed from WebText to modern training corpora? Now, WebText was 40 GB of Reddit linked web pages filtered by social signal. Modern datasets are enormous. They have code, math, books, papers, multilingual data, multimodal data, synthetic and model-generated traces, and so on. For example, Llama had like 15 trillion plus tokens. Huge scale of data shift. Now, next question. Was GPT-2 already an instruction-following assistant? No, this is key. GPT-2 is a base language model. It can complete text in task-like ways, but it is not trained to be helpful, safe, conversational, or instruction-following. That comes later. Supervised instruction tuning, RLHF, preference tuning, tool use, product scaffolding, and so on and so forth. Next question. Does zero shot mean the model has never seen the task? Not quite. It means no supervised fine-tuning on that benchmark. But the model may have seen task shift examples on the internet. Questions followed by answers, translation pairs, summaries, lists, explanations, and so on. The task behaviors emerges because those patterns exist in pre-training. Now, what's the deal with TLDR? In the summarization section, GPT-2 is tested on CNN Daily Mail news articles. And we spoke about how adding TLDR improves the performance. So, what was happening is GPT-2 is not a chat assistant. So you do not ask, please summarize this. Instead, the authors put the article into the context window and then add a TLDR at the end. The tiny text queue changes the task. The model has seen this internet pattern before. Long text and then TLDR, then a short summary. So it starts continuing in summary mode. This is why this section matters historically. It is an early clean example of prompting before modern instruction following models. So, finally, to conclude, what does this paper leave us with? The conclusion is simple, but historically very important. A large transformer trained on a large and diverse enough corpus begins to show zero-shot task transfer. That is the pre-training era thesis in one line. Paper 1 gave us the architecture, which is attention. Paper 2, this one, it says scale the data, scale the model, keep the same objective, and task behavior starts to emerge. But the behavior is still inconsistent, prompt sensitive, and far from assistant-like. So this paper gets us to the threshold. The next paper asks us how that threshold becomes a more predictable and usable system.